Hi guys, and welcome to this video on using recurrence relations to model linear and geometric growth and decay. I think that was the lesson. Anyway, my name's Darren from Maffs. Thanks very much for following. Behind me you can see the lesson objectives, which I'll go through in just a moment. If you can do me the honour though of subscribing to my YouTube channel. Why? Simply means that I know that other people are watching this video other than my mother. Alright, yes, hi mum, good to see you. But if you can subscribe and turn off notifications if you need to, it's going to mean the world to me. TikTok, I'm actually on TikTok. I know I always go TikTok, but I'm on TikTok. And all the notes that you see behind me, you can absolutely download from maffsguru.com, free to sign up. And hopefully really useful. In fact, print them off now as I go through the video because you can write all over them. Right, what are we doing? Lot in this lesson, right? And this is going to probably be a little bit of a longer video, but there's so much to cram in here and to understand. And if you smash this, Unit 3-4 is going to be so much easier, right? I'm probably just going to leave that behind to read if you want to. Pause the video, just to give you an idea of what we're actually going to go through. Now, in previous videos, we've looked at linear, arithmetic sequences and geometric sequences. Linear goes up in a line, either up or down. Geometric sequences go in a curve, either up or down. Now that's really useful. And again, anything that goes up must be growing and anything that goes down must be decaying. And I hate the word decay. It's a horrible word. But anyway, right, it reminds me of death and dying. Just gross. Could we not have thought of something better? Barry. Barry again. Leave that one there. If you don't know what I'm talking about with Barry, got to go and watch a few videos. We're going to build on this now, and again, linear growth. We've met before on our calculator that a linear growth, it's got the word line in it, means it is going to do this. If I was to plot the points for a line that's going to be linear growth, it may well look something like that. It's going to be a beautiful straight line. Grow, it's going to get bigger and bigger and bigger. Linear decay, in which case, will be a straight line going down. Put it in your summary book. It seems really stupid. Hopefully you've got this, but it's going to have some sort of real world examples. And believe it or not, if you have a bank account, then you are probably getting interest. Now, you're not going to get simple interest because if you are, you're being robbed. All right. Now, I know the banks have seem to want to take all my money anyway. But the point of it is, simple interest is where you get the same amount of interest month on month, regardless of how much you've got in the bank account. All right. So that there is an example of a linear growth. We are giving you the same amount of money month on month. Your bank account is going to grow the same. Now, what I want you to do is notice that this thing here is a recurrence relationship. How do we know it's a recurrence relationship? Because it starts with a V0 equals 2,000. It's got this V of n plus 1 is equal to V of n. That means to get to my next number, I take my previous number and in this situation add 150. So recognizing this as a recurrence relationship, really helpful. But what I also need you to know is that that number in front of the Vn, and you're going to go, there's no number there. What you talking about? There's no number. No, there is. It's the number 1. All right. Don't please forget the number 1. But because that's a number 1, it's linear growth. All right. And because in this situation that's plus 150, that is what is making it linearly grow. Whenever the number in front of the Vn is not 1, then we are going to end up with geometric growth. That's something to look for in a moment. Right, let's go to the question. The following recurrence relation can be used to model a simple interest investment of $2,000 paying interest at the rate of 7.5% per annum. Use the recurrence relationship to find the value of the investment after 1, 2, and 3 years. Now again, if we think about it, that V0 we can put into my calculator and then we can use A and S plus 150. So let's fire up my calculator. Let's clear everything that was there before. Actions, clear history. Right, what I'm going to do, 2,000, put in my calculator and we're going to do answer plus 150. And how many does it want? First, second and third year. So first, second, third year. Now again, with these type of questions, because we're dealing with finance, you'll notice that this is absolutely V0. That's my start amount. And then this here is at the end of each of my years. All right, so again, subtle difference. Normally we've been dealing with T1, T2, T3, but when we tend to deal with simple interest and money, it goes to V0. Right, so what have we got here? In the recurrence relation, find the value of the investment after 1, 2, and 3 years. So they're asking me to write V1 would be equal to, what do I have? 2,150. 2,000 300, got to get my eyesight tested, and V3 in that situation would be 2,450. Now again, you may turn around to me and say, but I can add on 150 every single time. That's fine, then add on 150, do it, that's not a problem. I'm just using the calculator to show people how to use the calculator. All right, B, when will the investment reach 2,750 value, 2,750. Well, we've already got the third year shown on the calculator. So what I really need to do is just keep going. 4, 5. So actually, 2,750 will be after, so for my answer for part B, would be after 5 years. Ka-ching. Nice and easy, loving this. All right, what are we doing next? Right, flat rate depreciation. Again, these are all terms that you should write in your summary book. Flat rate depreciation is where something reduces by the same amount every single year or month or period, okay? And again, we notice here, we've got a recurrence relationship. V0 is 18500. That's my opening amount. What's the context of the question, all right? He's purchased a car for $18,500, depreciating a flat rate of 10% per year, all right? So, V of n plus 1 equals V of n minus 1850. Now, you may be wondering, where on earth did we get this 1850 from? Well, it's actually 10%. Try that one again. It's actually 10% of that value there. So, when you work out 10% of that value there, you get 1,850. Right, use the recurrence relation to find the value of the car after 1, 2, and 3 years. So, we already know for part A that V0 is going to be $18,500. So we've got to now find V1, V2, and V3. How are we going to do that? Well, absolutely. Fire up my calculator. Let's clear what was on there before. Clear history. And what are we going to do? We're going to put 18500 into my calculator, and then I'm going to do my answer minus 1850. 1, 2, 3. And there we go. So just read off the values: 16,650. 14,800, 12,950. Right, now you don't include V0 here because that's how much they actually bought the car from at the very start of the period. After 1 year, it was 16,650, and so you've got to do V1, V2, and V3. Part B, again, how long will it take for the car's value to depreciate to 0? Right, now how do we do this? Well, I could actually just keep going. Let's see. So what are we? 3, 4, 5, 6, 7, 8, 9, 10. There we go. So luckily in that situation, just by hitting enter that many times, we can say that after 10 years, it will do that, right? Now again, there is another way of doing this, which is where you can sort of tie in the theory from before. I know that for an arithmetic sequence, I can change this into a rule. And what I now know is that for my arithmetic sequence, I know that V of m would be equal to 18500, that's my initial amount, minus 1850 times n, where n stands the number of times I'm doing it. All right, so after 1 year, we're taking away 1,850. After 2 years, we're taking away 2 lots of that. Now, what it wants here is it wants my final value to depreciate to 0. So we want this to be equal to 0. 18500 minus 18. Let's do my calculator off so this actually makes sense. 1850 times n. How do you find the value of n? Fire up my calculator again, and actually it's just solve it. So in that situation, I could do solve. 0 is equal to 18500 minus 1850 times n. I'm going to do comma n because I want to solve for the value of n. And there we go, out comes the value of n as 10. So in that situation, n is equal to 10. So there are 2 different ways of doing it for that particular question. Now, as I just said a moment ago, we can actually turn a recurrence relationship into a rule. And it is really, really important. As I said before, you know the difference. So in this situation, this here is my recurrence relationship. And what did I say? Well, my rule, my V of n, to find the value of my car after n periods or after n years or n months or whatever the question's on about, I always do my V0 value, 18500, and I subtract my difference or add on my difference. I would subtract 1850 times by n. So this value here is always v0, and this value here is always whatever is, you know, being appreciated or depreciated. And that makes life a lot easier if you can sort of understand what's going on. Now, what is important, as I've said there, is to notice that when you have a formula that has v of n plus 1 equals v of n plus some value there, then it is growing, right? Because we are adding on. That plus means it's getting bigger and bigger and bigger. That's good to know. When we have v of n plus 1 equals v of n minus some number, then actually that is going to decay, or, I don't know, go down, decrease. Right, so again, the slide that you can see behind me from mathsguru.com, you can download it, put it in your summary book. Life is good, but it's there as a reference. Here's an example. The following recurrence relation can be used to model a simple interest investment of $4,000 paying interest rate of 6.5% per year. Now again, if you want to know where this 260 came from, if I do 4,000 times 6.5 divided by 100, right, because that's 6.5%, divided by 100 to turn it into a multiplier. If I do that on my calculator, I'm going to get 4, 1, 2, 3, times, let's do my division there, of 6.5 divided by 100 gives me $260. So there we go. That's where that $260 comes from, just in case you ever want to know, because later on, certainly in General 3-4, you're going to have to do that. So can we read this? V0, there's my opening amount, was $4,000. To get to my next term, I'm going to take my current term and add. So this thing's going to grow because I'm adding. How much interest is added to the investment each year? So again, I can work this out, but if you understand how to read a recurrence relationship, it's going to be that last number there, okay? Trust me, it's that number there. So in answer to part A, doing a dollar sign is $260. B, use a rule to find the value of the investment after 15 years. So I've got to come up with a rule. Well, they've given me a recurrence relationship. How do we go from the rule? Well, if you remember, my rule starts with v of n. It always starts, the first number is v0, is 4,000. What am I doing? Am I adding on? I'm adding on, yep, because there we go. The 260 times by n. So we've got to find out then v of 15, which is going to be 4,123. Plus 260 times the value of n. What on earth is the value of n? Well, this little n down here is being placed in the 15, so my n is 15. How am I going to do that? Not in my head. Right, 4,000, 4,123, plus 260 times 15. $7,900. Now again, whenever you do calculations there, please make sure that you check that you've put a plus and not a times. The number of people who do a times is actually quite scary, and you get really crazy numbers. And moving on to part C, what do we notice? Right, use a rule to find when the value of the investment first exceeds $10,000. Right, I'm going to use this formula here. They're telling me v of n. It's got to exceed 10,000, but I'm actually going to let v of n be 10,000. So I'm saying, well, okay, let's find the value of n when v of n gives me 10,000. So that's going to be 4,000 plus 260 times n. Now I've got to try and find my value of n. How am I going to do that? Well, obviously I'm going to fire up my calculator. So I'm going to do solve. 10,123 equals 4,123 plus 260 times n, comma n. Now knowing how to use the solve function on your calculator is going to save you hours and hours of time. So when I hit enter there, I get a fraction. Now I don't want a fraction, I'm actually going to redo that as 23.0769. Well, we're not going to be doing 23.0769 years because it wants us to exceed this 10,000. We actually solved it for exactly 10,000. So for it to be more than that, we would want our value of n to be the next whole number up. So in which case, it would happen after 24 years. Now, knowing how to do that, as I say, is really important. I know I said this was going to be a long video. We're getting there, but there's a lot of stuff in here. Now, geometric growth and decay, remember, is not linear. So that's when it slopes up or it slopes down, all right? And that's when it gets faster and faster and faster, or slower and slower and slower. But again, the idea about growth and decay, same idea. Now, if you watch the early part of the video, you'll notice that I said when the value of v of n, the multiplier in front of it was 1, which we would just write as v of n, it's always going to be linear growth. Yeah, because whatever number we add on here, that's going to be the same every single time. When there is a multiplier in front, when there's a number other than 1, it's always going to be geometric. Whew. So in this situation here, if we have a look, we've got V0 is equal to 1000. So there's my start number. And to get to my next number, I take my current number and I multiply it by 1.08. Now, is that bigger than 1? Yes. Because it's bigger than 1, it's going to grow. It's not much bigger than 1, but it's absolutely going to grow. What do we got here? So, the following recurrence relation can be used to model a compound interest investment of 1,000, paying interest at the rate of 8% per annum. A, use the recurrence relation to find the value of the investment after 1, 2, and 3 years. Okay, so for part A, we want to find V1, V2, and V3. How are we going to do this? Fire up my cards, absolutely. Let's just clear down what's already there. Clear history. Right, so what do we want? I'm going to put 1,000 in, hit enter, and then I'm going to do answer times by 1.08. Now 1, 2, 3, and there we go. So first one is going to give me 1080. My next one is 1166.4. Now, because we're dealing with money, I'm going to put 0 there. I'll put some dollar signs in here because we want to make sure that the examiner understands we know we're dealing with money. And the next one would be 1259.71. All right, so there we go. That's how much is going to be in our account if we open it with $1,000 after 1, 2, and 3 years. When will the investment first exceed 1,500 in value? Now, again, I could use the formula. Let's do it the easier way of just hitting enter and seeing what happens. I want it to exceed 1,500. So that's after 3 years, 4, 5, after 6 years. So there we go. So just by hitting enter a number of times, all right, we know that after 6 years, it will exceed 1,500 in value. All right, now, and obviously not the one beforehand. Why? Because it's not over 1,500. Absolutely. Reducing balance depreciation. Now, reducing balance depreciation is, so again, what do we notice? We got here a situation where a car is purchased once again for $18,500. And we know to get to our next term, we're going to take our previous term and multiply it by 0.9. Now, because this number here is less than 1, it means it's going to get slower and slower and slower. It's going to be a decrease, but slower and slower and slower each time. So I use the recurrence relationship to find the value of the car after 1, 2, 3 years. Very repetitive. And believe it or not, these type of questions are very repetitive in exams as well. Right? Don't hold me to that, but there's only so much that we can actually ask you to do. So what I'm going to do here is put 18500 into my calculator, and I'm going to do answer times 0.9123. And there we go. We're dealing with money again. So dollar, I got 16650, and dollar 14985, dollar 13486.50. Yeah, not just 0.5, because we don't do that in maths. It's 2 decimal places for money. When will the value of the car first be worth less than $10,000? All right, well, let's just keep going. So what was that? 3, 4, 5, 6. Again, after 6 years. All right, so we could have done the formula way for that if I'd wanted to, but again, in this situation, probably just easier to hit enter, 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 enter over and over again. How do we turn a recurrence relationship into a rule for geometric sequences? Well, again, very similar to what we had before. The key here is in being able to read this. Now, as we had before, we always start a rule with V of n, right? Or whatever letter they're giving you. We start with a V0. Again, like we did earlier for the AP, or arithmetic sequence, yeah, we do the 1,850. But in this situation, because it's geometric growth, we know we have to look for my R. My R is my multiplier. Where on earth are we going to get this multiplier from? Oh, hold on a moment, there. Because it's multiplied by 0.9. So in that situation, it would be 0.9 to the power of n. So there we go. I have turned my recurrence relationship, which goes term to term to term, into a rule that now allows me to find any number I like. And again, practice makes perfect. So let's see, there is only one rule to be learned with this, as growth and decay are the same. Now again, growth and decay are exactly the same. When the value of R is greater than 1, it will grow. when my value of r is less than 1, it will shrink or it will decay or whatever. Now you're going to turn around and say, hold on a moment, you used a capital R here, why didn't we use a little r? Doesn't matter, right? For some reason the convention here it seems to be a capital R. It's not a problem. But when we have V0 as my starting value, then we have V0 here. Our rules always start with V of m, and then we just have to read that whatever value this is here in front of the V of n, that's what we raise to the power. The following recurrence relationship can be used to model a compound interest investment of 1,000 paying interest rate of 10% per year. All right, again, look at the multiplier. It's 1.1. If you've watched my previous video, you'll know that's a 10% increase per year. Use a rule to find the value of the investment after 15 years. Well, okay, we can find a rule. The rule starts with V of n equals V0, which is 1,000, times R, which is my multiplier. I've got that there. 1.1 to the power of n. So that's my rule written in terms of n, or my, but now I want to find V of 15. That's going to be 1,000 times 1.1 to the power of 15. All right, now notice it's not n minus 1 in this. I know that previously it was n minus 1. Now it's just the value of n. And I suppose that's where maths tends to confuse people. Bring up my calculator. What can I do here? So 1,000 times by brackets 1.1 to the power of 15, hit enter, and we get that that will effectively, after 15 years, grow to $4,177.25. Let's just put the dollar sign there so that we get the marks from the examiner, because we know we're dealing with money. And it's, again, reading these type of things is the key, really, being able to convert from one to another. What have we got here? Another recurrence relationship. Use a rule to find the value of the investment after 12 years. All right, well, again, that's a recurrence relationship. My rule, V of n, is going to have V0, 18500, times my multiplier of 0.9, times by, well, 12. Yes? Because we're looking for V of 12. Now, I've written V of n there, so let's change that to a 12, he says, cheekily. And then how are we going to do this? Oh, I don't know. Can't do it in my head. Do it in the calculator. Times, what do we have? 0.9 to the power of 12. Hit enter. Tells me that after 12 years, it'll be worth $5,224.95. Notice how repetitive these get? Put them in your summary book. Download the notes from Maths Guru. Trust me, I'll try and do everything I can to make life easier. And tell your mates if you can, and your teachers. You never know. They might find these useful. But there we go. That is the end of this particular video. Thank you very much for watching. It's been a lot. I know. How long is it now? About 25 minutes. Sorry about that, but there was a lot to go over, and it is so important for next year. But I'm going to sign off. Darren from Maths Guru. Sign up to Maths Guru on YouTube if you can. Just let me know you're watching. There's mathsguru.com and TikTok to follow as well. Otherwise, hopefully, I'll see you in another video. If not, you take care. Please stay safe.